This is Parents Podcast number 78, and today we're looking at the second half of this podcast series. Now we're looking at the effects of tornadoes on train aerodynamics. So in podcast number 77, we looked at how to make a tornado with trains in a wind tunnel. So now we're going to finish this off by looking at actually the effects of tornadoes on tornadoes on train aerodynamics. And again, like the last podcast, we're going to look at a paper called Experimental Study on Wind Loading Characteristics of Trains Under Stationary Tornado-like Vortices. This is open access, so you can find it in the link in the description. And I didn't put out a podcast yesterday, or a few days ago actually, on the 28th of December. That's because I was partly sick, but also it was Christmas. So I'll try not to cough my guts up in this podcast, but no promises. So let's get on with it. Now, let's look at the overall forces of a tornado on a train. So in figure 18, we have the effects of the train with different distances of the tornado with different distances from the train on the different forces. So we have the X force, X force, Z force, and different moments. Let's go through these. And they're also at a swirl ratio of 0.35. And if you remember from the podcast 77, the swirl ratio is just a good measure of the intensity of the tornado. So the higher the swirl ratio, the stronger the tornado is. Now, this is not a hard and fast rule because the swirl ratio is not exactly a measure of the strength of the tornado. To look at the strength of a vortex, you'd have to look at the circulation, but usually we do this in a two-dimensional plane. So that doesn't give you the strength of the tornado either. It just gives you the strength in two dimensions, like if you cut across the tornado. So the swirl ratio is a good way of looking at the general strength of a tornado, and it's characterized by the ratio of the tangential velocities, so how much the flow is moving around compared to how much is moving up. And the greater this number, the stronger the tornado effectively. So a swirl ratio of 0.35 is quite strong. It's also at a surface roughness of 0. So remember in the first podcast of this, we looked at different roughnesses, and to simulate roughnesses on the ground, they used these little cubes. So this is at a surface roughness of 0, so there's no surface roughness. So let's go into this figure and how tornadoes affect the forces on the trains. So it says that they have under the boundary layer crosswind conditions, they're represented by dashed lines. So they looked at not only the tornado, but the baseline, which is just a general crosswind. So the wind isn't swirling around, it's just moving in one direction. And they're represented by dashed lines. They say, for the result of the boundary layer crosswind, which is impacting the train, all of the 5 force coefficients do not change with distance because the boundary layer crosswind field remains constant with horizontal distance. That makes sense. Unlike a tornado, where the further you move away from the tornado center, the more tangential the actual train is to the flow when you think about it, and then the flow is more aligned with the train in that respect. With a cross-section flow, a crosswind, sorry, the angle which the flow is hitting the train remains constant. So you don't expect this to change going further away from the origin of the crosswind. And in fact, all the forces and moments, they're the same. However, for tornado-like winds, the overall force coefficient is significantly affected by the distance between the car and the tornado's center. So they say when they say car, they mean the carriage of the train. So when we say car, we just mean train. Near the tornado's center, at which the tangential velocities were extremely small because you're in the eye of it, the side force coefficient, CFX, was close to 0. So that makes sense. As the distance between the train car and the tornado center increases, the side force increases due to the combined effects of the pressure drop and tangential wind velocities. I should note that we're looking at the overall forces, but later in this podcast, we're going to go into the forces in more detail. So when we get to a distance of 1.5 away from the tornado center, which means that we're actually outside of the tornado, 1 means that's the edge of the tornado. 1.5 means that we're half again away from the tornado's edge based on the radius of the tornado. So the side force coefficient reaches its maximum value at this point, 1.5. So we're outside of the tornadoes by about 50%. And then it decreases with increasing distance. So there's this local maximum. The changes in the rolling moment coefficient were the same as those of the side force coefficient, though its values were approximately half those of the side force coefficient. So in other words, at the center, the rolling moment was almost nothing. And then when you get to 1.5. So you're outside the tornado by 50%. The rolling has this local maximum, and then it decreases back to zero as you get further away from the tornado again. They say the absolute value of the pitching moment coefficient increased first and then decreased with increasing distance. So again, it reaches its maximum value at 1.5. So it seems like 1.5 is the juicy range. But then it goes to zero when you go well away from the tornado. So when you're two radii away from the tornado's core, the absolute value of the pitching moment is almost nothing. So under the tornado wind loading, the lift coefficient and yaw moment coefficient of the train car exhibited the most unfavorable values near the tornado center. So that's completely opposite. So for the other values where we had the side force and rolling moment and the pitching moments, at the core of the tornado, these values were zero. But when you're at the core, the lift coefficient and the yawing moment coefficient skyrocket. They say this is mainly attributed to the strong rotational effects of the tornado and the large pressure drop at the tornado center, due to which the train car is subjected to strong upward section and counterclockwise torque. As the radial distance increases, the absolute value of the pressure drop decreases, which results in the lift and yaw moment coefficients dropping. So that's why we get that. And then when you get to 2 radii away from the tornado center, these values are almost zero again. So you can see that the forces on a train are very localized. Once you get 2 radii away from the tornado, all of the forces pretty much drop, whether it's the side force, the lift force, the rolling, pitching, or yawing moments, they all pretty much go to zero. So the effects of tornadoes are fairly localized to just the tornado's region, which is good in a way. So in addition to these overall forces, they looked at the effects of the swell ratio on these forces as well. And because the swell ratio, when you have a greater swell ratio, as I mentioned, you have a stronger tornado in general. So they looked at different swell ratios from 0.15 to 0.72. 0.72 means that the tangential velocity of the wind is 72% of the updraft velocity. So how fast the flow is moving upwards. And they looked at these swell ratio effects on the different forces. So the side force, the lift force, the pitching moment, the rolling moment, and the yawing moment. And what they found was that when the swell ratio increased from 0.15 to 0.35, the absolute value of all these coefficients increased slightly. When the swell ratio increased from 0.35 to 0.72, the lift coefficient and the yawing moment coefficient changed significantly when the distance of the car away from the tornado's core, was less than 1.5. But the other force coefficients remained unaffected. So in other words, again, the tornado's effects on the train are very varied, and only within 1.5 radii from the center of the tornado did they really have much of an effect, the different swell ratios. Outside that, they didn't have much of effects, and all these forces really went to zero outside this radii of 2 or 1.5 even. So the swell ratio does make has an effect to some extent, but not nearly as much as what you might think. In addition to that, they looked at the effects of the ground roughness. So as I mentioned in the start of this podcast and the last podcast, the ground roughness was achieved by making these little cubes that they put all around on the ground. And they range from 0% of the ground, so none of the ground had these surface roughness little things on there, to 25% of the ground occupied them. And in between, so that 0, 5%, and 25%. And this is how they measured the amount of roughness on the ground. The greater the percentage, the more rough the ground was. And it should be noted that these cubes, they are uniformly placed and they are uniformly sized, so they're all the same. Now, I should talk about the flow physics around a cube, because to some extent they would affect the flow physics that's hitting the train and then the flow physics of the train in general. So when you have a cube, you effectively have a von Karman coming off of it, especially when it's because of the sharp edges, but also over the top, you get separation on the top, and then the flow dives down after the cube. So you get the familiar von Karman, but over the top, you get this three-dimensional effect. And the amount that this flow pops up over the top and how long it takes for it to dive down depends greatly on the boundary layer thickness. So I actually have a friend who was investigating this quite a few years ago now, where he was looking at cylinders, and he was looking at rectangular cylinders, so cubes to some extent, or rectangular prisms, and he was looking at very short aspect ratios and very long aspect ratios. And he found that the different boundary layer thicknesses did affect how long it took for the uh, separated flow over the top to converge down, and also how much the flow around the top would separate, to what extent. So these cubes, the geometries of these cubes do make a difference, and I thought I'd just touch on that, so we do know about that. So on figure 20, they have the effects of the surface roughness, the ground roughness, sorry, on the different forces, and it ranges from smooth ground to 25%, and there's also 5% in there as well. So one, for the side force coefficient and rolling moment coefficient, they say it can be observed that as the ground roughness increased, the peak value of the side force coefficient decreased. So that's interesting. Higher surface roughness is possibly beneficial for reducing the side force. The position of the peak side force under different ground roughnesses were different. The side force coefficient reached its maximum value at about 1.5 radii from the tornado center when on smooth ground. But when you have 5% or 25% roughnesses, this maximum value was achieved at 1.2 radii. So instead of 1.5, it drops to 1.2. So you need to get closer to the tornado to get a higher side force. For the lift force, when near the tornado center, the lift force coefficient with rough ground was larger than that with smooth ground. In addition, at other positions, the lift coefficient decreased with increasing roughness. So when the train was 3 radii from the tornado center or more, the lift coefficient was almost unaffected by the ground roughness. So the pitching moment coefficient, when the car was located within the vortex core radius, the pitching moment coefficient increased first, then decreased with increasing roughness. So when the train was between 1.5 radii and 2 radii from the vortex center, the pitching moment coefficient decreased with increasing roughness. In general, the higher the ground roughness, the closer the position of the peak pitching moment coefficient to the center of the vortex core. So in other words, the greater the roughness, the closer you have to get to the tornado center to get the maximum pitching moment, which is similar to the lift coefficient in some respects. Or was it the side force coefficient? Sorry. The side force coefficient and the rolling moment coefficient. So the closer you get to the vortex center, the side force moment, the side force rolling moment and pitching moments all increase effectively, the maximum. So the yawing moment coefficient, when the train was within 3 radii from the tornado center, the yawing moment coefficient decreased with increasing ground roughness. But when you go outside 3 radii, it will remain unaffected. So again, not only is the tornado's effects very localized, but the effects of the surface roughness are quite localized as well in respect to the tornado's effects. So those are the overall effects of the tornado on the flow physics. Let's look into more detail now. So into the different aspects. Let's look at the pressure coefficient distribution. So they say in figure 10, they have figure 10 is contours of mean and fluctuating pressure coefficients distributions on the car surface. And this is at a SL ratio of 0.35 and no surface roughness. So they have just a typical boundary layer crosswind, as we mentioned earlier, where you just have a uniform flow velocity in one direction. Then they have the tornado with the train at the tornado center. Then at the edge of the tornado, so a radius of 1 from the tornado center. And then the train very far away, 3.75 radii away from the tornado center. So let's talk about what they're saying here. So under the boundary layer crosswind conditions, the pressure coefficients of the windward side of the train were found to be positive, so that the side facing the tornado. And that makes sense because you have all this flow that's hitting that side, and that means that you have a higher dynamic pressure, and that means you get a higher total pressure. The pressure coefficients on the upper and lower surfaces of the train car were negative due to airflow separation. So that also makes sense when you have flow hitting an object which has sharp corners. The flow is going to separate over those corners, and then the top and bottom are going to have separated flow. The pressure magnitudes on the lower surface were smaller than those on the upper surface due to the roughness of the ground. The pressure coefficients on the leeward side of the car were negative. and that makes sense because that's in a separated zone. And their distributions were relatively smooth compared to those on the other surfaces. So again, because you're in a fairly separated flow, there's not much going on. It's very uniform flow physics, so you would get a fairly uniform pressure distribution in that region. Now, comparing the upper and lower surfaces, they say due to the strong pressure drop at the tornado's core, significant differences in wind pressure distributions were measured between the upper and lower surfaces in the train. So the absolute value on the upper surface was quite high with 1.2, which is very high for a pressure coefficient. But on the bottom surface of the train, it was only 0.3. So that means that you're going to get a massive force because the lift, lift force because you have greater pressure on top, sorry. So that's going to be a downforce. Not thinking right with this cold. Anyway, so this pressure difference is going to create a downforce at this point. Then, when the train car was at the edge of the tornado, the symmetric wind pressure distribution disappeared from the over the surface. The mean pressure on the side surface closest to the tornado, so facing the tornado, increased since the tangential velocity was at its maximum here, and the radial and vertical velocities were also larger. Unfavorable values of fluctuating pressure were also found. On the other hand, the mean pressure on the side of the train further away from the tornado, so on the other side, these pressures were small, indicating that the pressure difference between the two sides of the train car were larger compared to when the train was in the center of the tornado. And that makes sense because when you have the train in the center of the tornado, you're going to have a symmetrical distribution on the left and the right because they're exposed to the exact same flow physics. It's just that one's on the left half of the tornado, one's on the right half of the tornado. So these are going to cancel out. But when you move the train further away from the center, you're going to get an asymmetry in the flow hitting the train. That's going to result in asymmetry in the pressure distribution over the train. So the facing the tornado is going to be higher because of a greater velocity, which means a greater dynamic pressure and greater total pressure. And the face on the opposite side, so away from the tornado, you're not going to have nearly as fast a flow, which means the dynamic pressure is going to be lower, and that means that the total pressure is going to be lower, which means you're going to get a lower pressure, and that means you're going to get a resulting side force pushing it outside of the tornado. So I hope that makes sense. So when the train car was at a distance of 3.75 times that of the tornado's radius, so very far away from the tornado, the absolute values of the surface mean pressure coefficients were small. So that makes sense. As you go away, the tornado's effects are very low. We saw that in the forces where the effects of the tornado on the train are quite limited. You need to be very close to the tornado, ideally inside the tornado. And I say this is due to the relatively small tangential velocities and pressure drops in the tornado when the train car is far away from the vortex core. Meanwhile, the fluctuating pressure coefficients were almost near zero as well. Again, that's because the tornado's effects are very small at this point. It's not inducing much flow. So that makes sense. So then let's move on to figure 11. So figure 11 is pretty cool. It has the mean pressure coefficients at the middle section of the train at distances from the tornado center of right in the center, then 0.5 times the radius. So still in the tornado, but sort of halfway between the center and the edge of the tornado. Then at the edge of the tornado, then 50% away from the edge of the tornado, then very far away from the tornado. And they have a bunch of them. So they say the pressure coefficients on the side surface facing the tornado increased first, then decreased with increasing distance from the vortex center. The maximum values were observed when the train was 1.5 radii from the vortex center, which we've seen before with the other forces. On the other hand, the pressure coefficients on the side surface of the train away from the tornado decrease with increasing distance from the tornado center. So on the one hand, the side facing the tornado sees this local peak when you're at 1.5 radii away from the vortex center. Either side of that, you will get a drop in this side, in this pressure on this side. But on the side facing away from the tornado, the further away you go, the lower the pressure becomes. So it decreases monotonically. On the upper surface, the pressure coefficients increase first and then decrease with increasing distance from the vortex center, which makes sense again. We've seen that before. And they reached the maximum values when they were at the edge of the tornado, though. So instead of being 1.5 radii, it was only at the 1 radius. So 1 radius. The variation trend of the pressure coefficient on the lower surface was the same as that on the side surface closest to the tornado, so facing the tornado. However, the values were lower. So in other words, the top and the side surface facing the tornado, we saw local maxima, and either side of this distance from the tornado center, you get drops in the pressure. When the train car was at the center of the vortex, the vertical loading was predominant and the side force was near zero, since the pressure distribution was horizontally symmetrical. And we covered that earlier, where if you have the train at the center of the tornado, you have symmetrical flow around it, so it's going to perform symmetrically. However, the top surface had a much higher pressure coefficient than the bottom surface. So when the distance between the tornado center and the train car started to increase, the horizontal symmetry of the pressure distribution gradually faded away. When the train was 1.5 radii away from the vortex center, the absolute pressure coefficients on the side surface closest to the tornado were distinctly larger than those on the surface far away from the tornado, which resulted in a large lateral force on the train car. Again, that makes sense. That was because of the differences in the velocity hitting the car. So in figure 13 now, we are looking at the mean coefficients of the middle section of the car for different swirl ratios, so different strengths of tornadoes. So they say the horizontally symmetric pressure distributions when the train is in the center of the tornado are shown. However, it can be seen that the absolute pressure coefficients at both the upper and lower surfaces increase with increasing swirl ratio. So the more intense the tornado, the greater the pressure at the top and the bottom. So similarly to the change in pressure drop within this range, the resultant lift force increased significantly when the swirl ratio changed from 0.15 to 0.35, but it decreased slightly when it changed from 0.35 to 0.72. So in other words, when you effectively double the tornado strength from 0.15 to 0.35, the lift force increased significantly. But when you doubled that strength again from 0.35 to 0.72, it dropped a little bit. So why is that? I'm not too sure, but I'm guessing it has something to do with how the flow is separating around the bottom and top surfaces. Perhaps when you have a stronger tornado, maybe that's helping the flow stay attached around the edges more. I'm not sure. If you do know, let me know in the comments below. But that's all that I can really think of at the moment. So they say the pressure distributions of the train when it was 1.5 radii away from the vortex center, so it's outside the tornado now, just a little bit, indicate that the absolute pressure coefficients on the side surface closest to the tornado, so facing the tornado, increased first, and then decreased with increasing swirl ratio. So that also follows the top and bottom surfaces. But the surface which is facing away from the tornado, as you go further, as you increase the tornado strength, this surface increased monotonically. So as you increase the tornado strength, the pressure on the surface increased continually. So in other words, the top, bottom, and surface facing the tornado all have a local maximum, and either side of that it drops. But the side facing away from the tornado just continually increases in pressure as you increase the tornado's strength. Now, let's look at the effects of the ground roughness. We looked at that a little bit, but let's go even further now. Let's break it down. In figure 14, the mean pressure coefficients at the middle section of the train for different ground roughnesses are shown. So they have ground roughnesses of 0%, 5%, and 25%. They say that it can be observed that the absolute pressure coefficient values on the upper surface increased first and then decreased with increasing ground roughness, and those on the lower surface increased slightly. So again, we see this local maximum forming. And it seems like tornadoes have a juicy point where you get the maximum forces at certain distances away from the core and at different certain strengths and at certain roughnesses. They say when the ground roughness changed from 0% to 5%, the resultant lift force on the train car increased. Whereas when you increase the ground roughness from 5% to 25%, the lift force dropped a little bit. And they say this effect is similar to the effect of the swirl ratio on the lift force. So when you put the car at 1.5 radii away from the vortex center, so just outside the tornado, it can be seen that the absolute pressure coefficient values on the side surface closest to the tornado, so facing the tornado, decrease with increasing ground roughness, whereas those on the other side decrease slightly. Moreover, the resultant lateral force on the train car decreased with increasing ground roughness. So somewhat of a stabilizing effect. Increasing the ground roughness made the train not have as great a side force, so it can sort of stay in position a little bit more. So when you put the train now at 3.75 radii away from the tornado core, so very far away, the roughness had no effect on, or no significant effect on the pressure distributions. So that's agrees with what we've seen in other forces and pressure coefficient plots, where the tornado's effects are very localized and you need to be within like 1.5 to 2 radii from the vortex center or the tornado center in order to really be affected. Outside of that, the effects of the tornado really drop very quickly. So in this podcast, make sure to like, subscribe. And if you're doing CFD, make sure to check out our courses to make you a better CFD. You can learn all the different tips and tricks. We have basic, intermediate, and advanced. So links in the description. I'll see you next podcast. Peace out, amigos.